Okay, so we are doing the air motion turning problem for video assignment 4 and the problem set 7. And here we go, let's read the problem. An airplane of mass 16,700 kilograms is flying in a straight line at a constant altitude and with a speed of 630 kilometers per hour. The force that keeps the airplane in the air is provided entirely by the aerodynamic lift generated by the wings. The direction of this force is perpendicular to the wing surface. Calculate the magnitude of the lift generated by the wings of this airplane, which we're going to indicate that as part A. To change the direction of this plane, its wings of the plane are banked 27.5 degrees to the horizontal. What is the radius of the circle in which the plane will be flying? Assume that the speed remains 30.0 kilometers per hour during the turn and that the magnitude of the lift provided by the wings is unchanged. We're going to label that as part B. What is the magnitude of the vertical acceleration that the airplane experiences as a result of the turn? We'll label this as part C. Okay, so based on this, we can already tell that part A is going to have a different scenario, and part B and C are going to have another scenario together. So let's look at part A. So part A, we have a picture here, and we only indicate two forces on it. There's no centripetal force because that only comes in part C, since the plane is not angled. It is going in a straight line. Currently, it's not turning, it's just going in a straight line. So there's really only two forces acting on it, assuming no air resistance. There is the force of the lift and the force of gravity here, and then there's the velocity, which is going straight. Okay, part B and C's picture can be indicated by this. So I drew this kind of a coordinate system, and it looks sort of like a free body diagram, but I'll explain why in a minute. So we have three forces affecting here, which is the force of the lift, which is perpendicular to the plane still, so keep that in mind of the direction it's going in. The centripetal force, which is directly right, and the force of gravity, which is directly down. So now that we labeled this, look at how theta is banked right here below the wings, and then look at how this corresponds to this angle vertically. It gets the vertical angle here between this, and I'll explain more with the free body diagram. And then we use the vertical angle theorem to basically connect it to where this goes into here, and these are the same angles. So, what does all this mean exactly? Well, let's go to the first free body diagram. So this is the first scenario, part A. So here we have two forces, same magnitude, only a velocity change, so there is no net force. FL is equal to FG. Okay. And then with the second free body diagram, we are indicated FL and the direction with the magnitude, which is relative to this, to the Y here, to the theta. And then we have FC being directly on the right of the axis and MG being down. So looking at this, we do not tilt the axis like we usually do. And the reason for that is mostly to lessen the complexity of this problem. Since we noticed that FG and FC are going in like completely straight directions relative to the observer's eye, we would just want to keep this the way it is, with just FL going to the right. Okay, keeping this in mind, we have theta now going to this dotted line. So what is this dotted line exactly? Well, that dotted line actually points to the left, and that's the lift force, which is counteracting the centripetal force in this case. So what do we define that as? We define that lift force as FL sine of theta, because it is the opposite here over the hypotenuse. Okay, and then the y component, which we'll solve later in part C, will be FL cosine theta, and the cosine is, the reason for that is because it is adjacent to this angle over the hypotenuse. Okay, so let's look at our knowns and unknowns. So here we have many variables that are used for both scenarios, with a few exceptions of the centripetal force, which is not existing in scenario 1, and the radius not existing in scenario 1 as well. However, we still need to find these unknowns. We don't know the force of gravity. We need to multiply m times g. We don't know the lift force. We don't know the centripetal force of the second scenario. And we don't know the radius. Okay. Now that we've defined the knowns and unknowns, here's what we need to do to solve the problems. First, we need to find the lift force of the airplane. We can do this by finding Fg through the equation mass times gravity. We need to set the net force equal to the lift force minus the force of gravity. Also recognize that the net force is equal to 0 because there's no acceleration going on. It's just constant velocity. Then we need to solve for the lift force. Okay. Second, we need to find the radius of the circle of the plane. Convert speed to meters per second, because keep in mind that that speed we were given was kilometers per hour, and we don't usually convert those, or we don't usually use those units for the given units of the other variables here. Then we need to set the net force of x, being equal to the lift force times sine theta minus the centripetal force. Okay? Then recognize that the net force of x is also equal to 0 in this case, mainly due to how it is still constant velocity being assumed in that problem. Solve for the centripetal force. Then we need to set the centripetal force equal to mass times the acceleration, and I'll get into this in a minute, acceleration of c, and the c being the centripetal acceleration. So what is A defined as in this case? So since it is centripetal acceleration, meaning it's in a circular motion, we need to define that A is equal to v squared over r. So plug that in, and then we get Fc being equal to mass times velocity squared divided by the radius. Afterwards, we solve for r. Third, we need to find the magnitude of the vertical acceleration. We can do this by finding the y component of the lift force with FL cosine of theta. Set that equal to mass times the acceleration of y. Solve for the acceleration of y among this lift force. Then we can set the variables of the net force of y equal to force of gravity minus FL of y. We can cancel the masses in this case. Then solve for the y component of the net acceleration. All right. Okay, let's get into this. So here's part A. So in scenario 1, we're trying to find the lift force. So here we have force of gravity equal to mass times gravity. We were given that the mass is 16,700 kilograms, and the gravity is 9.8 meters per second per second. Multiply these two and you get 163,827 newtons. Now keep in mind that the net force is equal to 0. And use the equation F net is equal to the lift force minus the force of gravity. Plug in the values that we know, and then solve for FL. And then FL should equal to 163,827 newtons. Part B, we're now implementing scenario 2. We need to find the radius. Okay, let's do the conversion of velocity first. So here we have this little table here, and we need to convert hours to seconds. Well, there's 1 hour in 3,600 seconds. So now we can cancel the hours based on this multiplication, or division in this case. Same thing with kilometers, except set the meters on top and kilometers on the bottom. Cancel out the kilometers and recognize that there is 1 kilometer in 1,000 meters. Cancel that out, compute the function here, and we get 175 meters per second. All right, now we have the net force of the x component being equal to the lift force times sine of theta minus the centripetal force. Okay, let's solve for centripetal force. Also recognize that F net is equal to 0. F net of x. When we solve for the centripetal force, we now are given that centripetal force is equal to the lift force times sine of theta. Plug that in, we get 163,827 times the sine of 27.5, which is equal to approximately 75,646.89 newtons. Now that we have that, we can plug this into Newton's second law, and being mass times acceleration, or in this case. The centripetal force is equal to mass times velocity squared over r, plugging in v squared over r inside a of c. And now we solve for r and plug in all the values. We get r equaling to 6,760.85 meters. Okay. Now we have part C. Part C, we have the acceleration of y, of the net y, and now we have the lift force being equal to the lift force times cosine of theta, what we mentioned earlier as the y component of that lift force. And then we plug in the numbers, and we should get 145,469.78 meters per, meters per second per, wait, hold on. That's the lift force of y. Okay, now we plug in, or we implement Newton's second law, being mass times the acceleration of y, and then we do 145,469.78 being equal to 16,700 times the a of y. Plug all that in, or solve for a of y, and then we get approximately 8.7 meters per second squared. Okay, now we set up this equation with each other. We do that F net of y being equal to force of gravity minus FL of y. We put in all the variables that they're equal to, and then we try to get masses by itself, and we cancel the masses, or undistribute the masses from the quantities of the forces here. Then we have a of y being equal to g minus a of FL of y. Plug those in. We get a of y being equal to 9.81 minus 8.70, and approximately we get 1.11 meters per second squared for part C. Okay, checking this, to check part A, we just need to see that F net is being equal to 0. So plug in the values FL minus FG, which should be the same, and then we should get 0. For part B, we have the centripetal force. Make sure the centripetal force is the one that we were given earlier, which plug in all the numbers with the new radius, and we got the number. And then, but that's not the only thing we're going to check. We're also going to check that FL sine of theta minus the centripetal force is also equal to 0, because we did define that the F net of x is equal to 0 earlier. Plug everything in, we should approximately get 0 as well. Okay, and then for part C, we just need to plug in that F net of y with our new acceleration of the net force is equal to the value given on the right side of the equation. So yes, we plug that in, and we get 18,537 newtons. And that is everything for this solution.